I see it. Okay. So I'll start. Okay, so hi everyone. So today's lecture is on grids. I am like planning to keep it a bit low tech than the like previous two lectures. So okay, yeah, let's start. Uh, so in grids we'll like deal with a lot of problems where we will like say we will place tiles or dominoes or tokens on these cells of a say m cross n grid, and we'll see some general methods to like deal with problems of that sort. So something a classical problem which I think a lot of you might have already seen. So the opposite corners, okay, two opposite corners of a 8x8 chessboard are removed. Can the remaining board be covered with dominoes? So yeah, does anyone know how to solve this problem?
Yeah, that the our we can say our domino cover exactly one black and one white, and if the corners will have the same colors, right? And then
Okay,
uh,
yeah, yeah. So that's basically how the solution works. So I'll just tell you what he said. So like think about it how a chessboard generally looks like, right? So in general a chessboard is like you have squares of alternating colors, right? So you have a black, okay, this is green here, but okay, and followed by a white and then another black and so and so on, right? So if you like think of it in grid notation, so like suppose I say that my like lowest bottommost leftmost bottom square is like the 0 comma 0 square, right? Then you'll say like suppose this is black, right? And suppose then this is white. So what I'm trying to say is basically the chessboard coloring works in a way like you have black white alternating, and you have 32 black and 32 white squares over the board. So now if you think about what a domino does, is a domino is going to cover one black square and one white square, right? So in other words, it's always going to cover like one black square and one white square. So it cannot cover like like squares of the same color. That's basically the main point of this coloring. Okay. So now look at something. So how do you think of this coloring? Let us say you draw the coloring for a smaller case. So suppose you do it for 4x4. Okay. So suppose this is 1, 2, 3, 4, 2, 3, and 4. Okay. So suppose you start with, so suppose I'll write 1 for black and I'll write 0 for white. Okay, so just so that I don't have to shade it every time. Okay, so suppose you start with black at the bottommost, leftmost bottom cell, and then you have 0, and then you have a white, and then black again and white, and then you just do it. 0, 0, 0, 0. Okay, so now note something, that these two cells and these two cells are the opposite corners, right? But note that the opposite corners have the same color. So when you remove them, so suppose I remove this one and this one. You're left with something like, in this case, you have like 8 whites, I think, and 6 blacks, right? Yeah. So you cannot cover with a domino. So you can't cover them all. And why is that?
Okay,
Because
so
every,
basically we are
yeah,
referring to a 1 into 2 block as a domino, right?
referring to what? Yeah, right.
Or
Yeah.
a
So
1
this
into
is a,
2. Yeah.
yeah. So this is a domino. Yeah. Okay. So are there any questions regarding this then? So how the proof works is like we need to figure out a nice way to think about a domino. Okay, so like what can we say about the squares like a domino occupies, and a nice way to think about them. So the way we do it is basically impose a black white ordering or a black white coloring of the cells. Okay, and we see that a domino always like covers one black cell and one white cell, right? And so we see that whenever like we have an 8x8 chessboard, the opposite colors have like opposite colors, opposite ends have like the same colors. So when you take them out, so you are left with like something like 32 whites and 32 black and 30 white. Okay, so obviously you cannot color them with dominoes, because dominoes is also always going to do like one black and one white. Okay, so any questions regarding this? Okay, so if there are no problems, I'll move on. So in the above problem, we used something which is like coloring of the board, right? So the most like simplest type of coloring is the black white coloring. So coloring is going to be quite important for us, like in a lot of grid problems. The simplest form of coloring is the black white coloring, which is also the sort of the mod 2 coloring, right? So why am I calling it mod 2 coloring? Okay, so suppose you think of it like, so suppose you had a 4 by 4, right? So suppose you number the squares, number the rows and the columns as 1 2 3 4. So yeah, so suppose this is the first column, 3 4 1 2 3 4. Okay, so and suppose this was your chessboard coloring, 0 1 0 1 1 0 1 0 0 1 0 1 1 0 1 0, where 1 stands for a black and say 0 stands for a white. Okay, so then note that we can write like every cell is given the color x plus y mod 2, where the cell is say x comma y. Do you agree with this? So something like, look at the cell 2 comma 3, right? This is this. So 2 comma 3 is 5. So like 2 plus 3 is 5 mod 2, which is 1 mod 2, right? So since 1 was black, so we colored it black. So does this make sense? So black and white coloring is basically a kind of a mod 2 coloring, or a so this is basically a kind of coloring where you are going to use parity arguments. Parity is basically just mod 2. Does anyone have any questions regarding this interpretation of the black white coloring? No. Okay, then let's move. So in more so what else kinds of colorings can we use? So just generalizing from mod 2, we'll see mod n colorings. Once again, note that these colorings are just going to help you like think about some aspect of the problem in a better way. So the colorings are done in such a way such that there is some sort of periodicity associated with them, and often colorings can, if you spot colorings, they can lead to very smart solutions to problems. So yeah, so this is something. Okay, so let's do one problem first. I'll come to modern color. I will elaborate on modern. I'll show problems on modern coloring after a while. So let's do a couple of problems on black and white covering first. Okay, so you know what a knight is, right? The chess piece. So like a knight always moves like two piece. Okay. Okay, I'll just draw another grid. Let's just draw 4 by 4.
2.5.
Yeah, it moves by 2.5 pieces, right? So if it starts from here, it can go to here, or it can go to here, or it can go to, I think, here. Yeah, and the other end is blocked, so it should have been able to go to here somewhere, but it's blocked. Okay, so basically a knight moves like sort of 2.5 moves. Someone described that was, oh, that was a good description. Okay, so I'll tell you a problem. Does there exist? I'll explain the statements immediately. Does there exist a closed knight tour on a 5x5 chessboard? So what do I mean by a closed knight tour? A closed knight tour means the knight starts somewhere and moves to every other square, and okay, and let's say starts somewhere and visits every square of the board exactly once. Okay, so what I mean by this is, like, suppose the knight started here, okay, and then it moved to here, okay. Now it cannot move back to here. This is not allowed, okay. But it can go from here to say something like here, and then go from here to something like here, okay. So the question is, does there? So this is called a closed knight tour. If you allowed like it to jump back to its original location, that would, I think, be called open knight tour. So the question is, does there exist a closed knight tour on a 5x5 chessboard? Does everyone get the question? What I mean by a closed knight tour?
So should it cover all squares of the chessboard?
Yeah, it is supposed to like cover all the squares of the chessboard.
Okay.
Like it starts somewhere and then it makes a sequence of moves such that it visits every square of the chessboard exactly once. And the chessboard is like a 5x5. Any ideas? I'll just draw 5x5 for your convenience.
It should return to the starting position also, right?
No, it doesn't. That is the point. So like if it, okay, so suppose there would exist
No. I meant like it covers 25 squares. So is it necessary that when it reaches the 25th square, like the last square of its tour, it
yeah.
should be again it should again be able to jump on the first square from where it started? Like what I mean is, we are covering 25 distinct squares, right? So like I am
Yeah.
starting from some square, and then I'm
Yeah,
arriving
you are
at
supposed
some
to,
point.
yeah, you are supposed to, yeah, sorry, okay, yeah. I'll just mention that as well. Yeah, sorry. Yeah, so you should be able to back to initial square from final. Okay, so oops. So what he said was like, so suppose I'll just define the closed knight tour again. So
Is this not
this,
somewhat similar to how we define a cycle in graph theory? Like we choose a point and then we are supposed to go back to the initial point.
Yeah, it's kind of the same, but like, okay, just trying to keep it more down to earth sort of. So like you start from somewhere and you like make a sequence of moves, okay, and you come somewhere and suppose you visit every square exactly once, and then suppose and you should and then you can like say go back to the initial point. So that is a closed night tour. Yeah, kind of missed that out. Sorry. Otherwise, it's not
Okay,
closed.
so then it's not possible
Yeah, why is that?
because the last and the first would have the same color.
Come again?
The last position and the first position of the knight would have the same color.
Okay,
So you
and why
can't
is
count
that?
from the last position
And why is that?
because at, at every step, the color of the square on which the knight is changing.
Okay. And how many moves are you making?
25.
25 is
24.
odd, yeah. Like, okay, yeah, if you go back to the original, that's 25. Okay, yeah, cool, 24. So yeah, I'll just say what he said. So consider a move of the knight. Okay, uh, so you need to okay. So consider a move of the knight. Just draw the 5 cross 5. Yeah. So suppose the knight started here, and now it can move to here, here, and here, right? So now consider the black and white coloring once again. Okay, so I'll just use a green for black because I'm out of colors. So this is green. Uh, so do you notice a pattern here? Like, so whenever the knight makes a move, it changes the color of its square. Right. So, like, look at this. This square is white, right? But then this square is black. This is also black, and this is also black. So all its possible neighbors are black. So you can like write this out sort of using the x plus y mod 2 notation. So basically, this happens is like whenever you are making a move for the knight, it is going to change the color of the square. Okay. So now think about this. So suppose you had a sequence of moves that like you visited every square exactly once and then you came back to the original position. Okay, so that is 25 moves in total, right? So now think about it. Suppose you were on a white square. Okay, so then after 25 moves, every time your color of the square changes, right? So after 25 moves, you should land on a black square, and hence this cannot be done. Does this make sense? Does anyone have any questions regarding this? I'll just repeat what I said anyway. So like we saw that using the chessboard coloring, okay, when you have like just a black white coloring of the board, whenever the knight moves, it is going to change its direction, so change its square color. Okay. So now suppose there was some cycle and it started from a point and then it visited every other square exactly once and then it came back to its original point. Okay. Then suppose the initially it started on a white square. Okay, suppose WLG it started without loss of generality. It started with on a white square. Then every move it is changing its square color, but it is making 25 moves in total, right? So 25 is odd, right? So every time you make two moves, you return to the same colored square. So like you have like 12 pairs of two moves and 12 pairs of moves and a final move at the end, right? So the final move is going to change the color of the square. So yeah, so if you start at white, you will end up at black, but that obviously isn't possible, right? So you can't have a the closed night tour.
Like if we make a move by placing a knight on a even number, like any even number 1 2 3, like any 1 2 4 or something like that, then we can have
Okay.
the graph connected with at least one vertex isolated, right? But if it is moving from odd number, then if we want to cover every part of that, then we will have the graph to be not connected because we'll end up in a loop, right?
No, I don't really say. Do you mean something like if we allow the knight to miss one vertex, if we allow the knight to miss one square, then the closed then the sorry, the closed knight tour is possible, as if you allow one square to be missed. Are you that? I didn't exactly understand what you meant.
Okay, let me think about.
Okay. Yeah. So any questions
Also,
regarding this? Yeah, go on.
also, is it known, like if we remove that condition to return to the initial position, then is it possible?
Yeah, I
So
mean,
it
I think
covers
it
this
is
as
possible.
well.
You can just, I think it is possible that the open night tour exists, and like you can just Google Wikipedia for that. So if you just Google closed night tour, so the first animation on Wikipedia is the 5x5 open nights tour. Yeah, it does exist.
No, I
Okay.
was asking that after 25 moves, I think it should be land on a white square. Then we can say, right, that after it is landed on white square after 25 moves, now it cannot move to its initial position at its every time changes its color.
I don't really, no. It's like after 25 moves, it is supposed to return to its initial position, right? Like it's after 25 moves, it's supposed like every move you're visiting a new cell, right? So after 24 moves, you are supposed to have visited the last cell, which wasn't visited. Okay. So when you are making the 25th move, you must return to the original cell. Now, what we see
Yeah,
is that okay, suppose the original cell was white, but you now see that after 25 moves, it should be black according to our. So that is so. Any questions regarding this? Any more? Okay, then if there are no doubts, I'll move on. Okay, let's do that. Okay, so next problem. Suppose one square is removed from a 2 power n cross 2 power n board. Prove that the remainder can be tiled with L dominoes. So just if okay. L domino is basically structure. Okay, so the question tells you that suppose you have removed one square from any 2 power n cross 2 power n board. Prove that the leftover board, that is the with 4 to the power n minus 1 squares, can be tiled using L dominoes. By tiled, I mean like you can just place L dominoes in such a way such that the board gets covered. Yeah, so any ideas about how to do this? Okay, so suppose you first
Induction
let's just
seems one way.
induction sounds good. Okay, so induction sounds good because maybe you can solve for a easier case and somehow just carry it over to the harder case. Okay, so let us first solve the problem for n equals to 1, right? That is just a 2 cross 2. So just n equals 1. So you had like 2 cross 2, and suppose I deleted this square. Black means deleted. Okay, so now this is easy, right? You just like place the domino like this. Okay, so this was easy. Everyone gets how like the n equals 1 case works. You just delete one square and then you can just put the domino as you like. So now what about n equals 2? Maybe that is a bit harder.
uh, the deleted square must belong to one of the four 2 raised to n minus 1 cross 2 raised to n minus 1 grid.
Okay, yeah, let's see. 1 second, I'll just draw. Let me draw the first. This is kind of hard to draw it here. Okay. Okay, let's see. First, let's delete a random square first. Let's say I am deleting, I don't know, this one. This square isn't present anymore. Okay. So how do we go about this? I'll number the squares for your convenience. So if someone wants to tell me where to keep a tile, they can just do this. Yeah. Any ideas on how to go about this problem? How to tile 4 cross 4?
Yeah, I think if we could prove that in a fully 4 cross 4 chessboard, or we can not chessboard, in a tile board, we can when we tile the domino, there will be exactly one square left in a fully 4 cross 4 tile board. So if that square is removed, that
It's not help, right? Because see, what you are trying to prove that whenever you tile a 4 cross 4 with L dominoes, you will have one square left. But you are not telling me about what is the set of all the squares left. So basically, the problem tells you that no matter which square you delete, you can always tile the remainder. Okay, so what you are telling me is that whenever you tile it, one square remains. So you are not proving something like so. After you prove, there might be something like there might be a special location of a square after which you remove, but you cannot tile it at all. Okay, so something like that. You're not, like whatever you're trying to prove is not equivalent to what the problem is telling you. Do you get the thing?
yes, okay.
Okay. So let's just solve the n equals to 2 case for now. This is quite insightful actually. This will actually tell you how to go about the general case. So anyone want to tell me where to place a tile?
I think someone in the chat said place an L-domino in the top right to cover the corner square.
Okay, sounds a good idea. Okay. Oh.
After that, we can make a reflection beneath the black one.
Beneath the black one as in reflection as in?
As like 5. It will form a type of 5.
This?
No, not like this.
Okay.
Like beneath
Can
the
you
black
name the square?
Yeah.
Can you name the squares? Yeah.
4, 2. 4,2.
Okay, here.
Yeah,
Then?
yeah. Okay.
And which one?
And 4, 1. Yes.
Okay.
Yes. And then 4, 3. Sorry, 3, 1.
Cool. Yeah. And
then the middle ones, the middle 3 ones.
Middle 3 ones as this.
Yeah, this one. Yeah. These 3. L. Please form a simple L.
Okay.
Yes.
See, I see.
Yeah. Then that. Yeah.
Okay. Cool. So okay, let's do another n equals 2, because n equals 2 can have a lot of variations, right?
Yes.
When you're trying to solve the n equals to 2 case, think the n equals 1 case to solve it. Okay, so n equals 1 case was easy. Try to see if that you can carry it over somehow. Okay, let's do this one. Okay, yeah. Let's delete this. So okay, now how do we do it? Yeah, where do I place the domino now?
Yeah, hello.
Yeah, go on.
The topmost left one.
This?
Yes. Right.
Okay.
Then
And?
beneath, continue the straight line.
Yeah, and then?
Then
This.
again the middle ones. Yeah, that also. Yeah, same thing. Yes.
Okay.
Yes.
So does anyone see anything in common in the two things?
We started from the corner.
So,
Uh,
go on.
the middle one and the right one is a reflection types.
These two, you're saying. Oh, sorry. Middle one and the what? Right one. Reflection as in?
Like the point at 2, 2 and the point at 3, 3. When we
Point
reverse it,
at
diagonally.
2 and point at 3. Yeah, you can just reverse the thing. Works. Yeah, I understand what you're saying.
Yeah,
Okay,
yeah.
so let's say something like this. Okay. One second. Okay. Sorry. Yeah, that's it. This is gone. Now what do we do?
So we can start covering it from the right upper right corner.
I can't hear you. Can you be a bit louder?
We can cover it like 4 4, 4 3, and 3 3.
Good. Okay. Then
It's somewhat similar to the first case.
No, then to 4, 2, like place this L beneath the L.
something like this.
Yeah,
Or okay. Just tell me the coordinates of the squares.
yeah. Like the first point at 4, 1, 4, 2, and 4, 3, 1. 4, 1, 4, 2,
Okay.
and 3,
Okay.
1.
This
3, 1, 3,
3
1.
1. Okay. Sorry.
Yes. Then the middle ones. Then and a simple L and the middle ones. Yes. And then, yeah.
Then it's basically it's force. So anything you see like in anything common from the three that we have done till now. So can you see how you can use the n equals 1 case to go from to solve the n equals 2 case?
Yes.
Okay, go on. Go on. You're saying something?
No, not now.
Okay.
We are starting with the corners
Take a
and
look at what we
reflecting
are
eyes.
starting at the corners and
Then reflecting to the other corner diagonally.
connecting to the other corner. How does that
And then
work?
tidying the circle.
No, like this is not reflecting, right? So this and this are not reflections. The reflection will be something like this. That is not what we are doing. Okay, so let's
You
think
seem to
about
have
it
a
this
central
way.
domino.
Come again.
They all seem to have a central domino in the middle.
Very good observation.
And one more observation is that the four of them form a boundary-like structure when the grid is in the four of the central grids, while the dominoes
So
without having
something like this. So something like this. So this is a kind of a boundary. I think this is what you're saying.
yeah, when they are in the middle force, then it is like the corner dominoes
Go
form
on.
a boundary-like thing.
Good idea, actually. Okay, so think about it like this. Okay, actually, whatever they said was actually good. So suppose you are trying to always think about whenever you are trying to induct, always think about how to go from the smaller. Okay, so now I'll show you like how to do it. Okay, so suppose you have like another grid, right? 4 cross 4, curved lines in a row?
I think like when we move when we remove a square from the grid and like
Yeah.
we go from even number to odd number, we are just
Okay.
replacing the vertices, right? Diagonally.
Replacing the vertices as well?
Yeah, in the n is equals to 2 case and the last case we have checked. This is the similar, right? Only the first one is
I
changing.
don't really understand what you mean. Okay, actually, give me a second. My voice started echoing. I'll just like disconnect my headset. Hello. Hello.
Hello.
Yeah, you're audible.
Okay, cool. Yeah. So what were you saying?
Like we initially have that L terminal, right? In the second n is equals to 2 case.
Yeah.
So we have the second row and the last one, we have removed it. So what we are doing is we are diagonally removing the opposite, like the diagonal square of it in the last one. So we are just switching that vertex to the one which is before, and similarly that happens to every diagonal vertices, and we are drawing the lines in a similar positions,
So
so
you're
that
saying
every other
like,
domino.
oh my God, my voice is echoing so bad. I'm really sorry about this. Give me a 1 minute. Hello, hello.
Yes, you are audible.
Yeah. So what happens is like suddenly my voice starts echoing and it's so like so annoying. Okay. Okay. 1 second, I'll reshare. Uh, okay. Is the screen visible?
Yes.
Okay. So what I was going to say is like, suppose you have any square blocked. Okay. So suppose you have like this square blocked for now. So think about it. So someone mentioned the idea of the boundaries, right? So suppose you can think like these two middle lines sort of divide the square into 2 cross 2, 4 2 cross 2 blocks, right? So think about this. I know that whenever I remove one square of a 2 cross 2, I can always style it with an L termino, right? So now think about it like this. So whenever you have removed one square, it must belong to one of those 4 subgrids, right? So suppose in this case, so you can just now you know that for this subgrid you have removed one square, so you can always style it with one L termino, right? So this termino is kind of force. Okay, so this is something we'll do because we are thinking inductively. Okay, so what do we do next? So oh, so think about it again. Okay, three grids which are 2 by 2, and we need to remove one square each of them, because we know that whenever we remove one square from a 2 cross 2, we can cover the rest with an L termino, right? So can you think of a way to remove the L to remove one square from each of the three grids? Someone had pointed out that, okay, so can you okay, let me like give you a minute to think about it maybe. Okay, so the question is how to remove three squares, one from the three subgrids, three full subgrids. Does the question make sense?
Yes.
Okay, so can you You can now make these subgrids as 2 cross 2 minus 1 cell. So you have 3 squares, right? And L Tromino also has like 3 squares. So does that give you a hint?
Yes.
Okay. So
Yeah. So we will remove the 3 3 and 3 2 squares.
yeah, and this,
And
right?
along with the 2 1 square.
2 2. Okay.
2 1.
Okay. 2 1.
Yes.
Yeah, and
And 3 2 and 3 3.
that is not a Tromino. Like, how do you just remove it?
When we
How
put
do
the
you remove?
central 4 grids, we can remove so that we get a domino and we can connect them.
Yeah, that is the idea, right? Like whenever you are trying to here, what does remove mean? You cannot like actually remove them, right? Because the problem is telling you can like delete one cell from 4 cross 4. Remove as in some way you have taken care of 3 squares from one each from each of the 3 full grids, so that you don't have to worry about them. So can you think of a way to like do that? Also, can you turn off your
Yes,
volume?
so like there is always a middle square from which one of the squares is removed, right? When we cover the square with the dot, like the which is removed, there is a L Tromino, and we have completed the square. If we consider the square which is in the middle, like for
Yeah,
that
this
square, there is one
like
of the
this square.
Trominos.
Yeah.
Yes, for that square,
Okay.
there is one of the
So
Tromino which
this
is always removed,
a
like
central
covered from the
Tromino,
Tromino.
a sort of a central
Yes.
Tromino, right? Yeah, that is the idea. So what he said is like, suppose you have, I'll just draw once again. Yeah. So suppose you have the 4 cross 4. So suppose this was the cell where the initial deleted cell on, you have taken care of this cell. Okay. So now what we will do is like, suppose this and this. Yeah. So now what we will do is like, suppose this part has been taken care of. Okay. So what we will do is we will introduce a domino here. What does this do is now in each of the remaining 3 full subgrids now become now have one cell deleted from each. One cell deleted. What does deleted mean here? Deleted means you don't need to worry about them. They're as good as deleted, right? So now you can just like keep putting dominoes of the form this, basically just inductively thinking. You are just fulfilling like how you do for n equals 1 case, right? So this n equals 1 case, you have this one covered. So I mean deleted, this one deleted, so you can just cover this and so on. Okay, so see how to go. So now can anyone see the general case from here, how to go from n minus 1 to n using this intuition, how we like where we went from 1 to 2? Can you see how to go from n minus 1 to n?
Yeah, like we divide it into 4 squares, and then we can complete one of them, and the rest 3
And
which
the
is
central
in the
domino.
central can be covered, and then we can induct and complete it like step.
Yeah, that is the idea. So what we are saying is basically you can think of 2 cross n as 4 subgrids, sorry, a 2 cross n cross 2 cross n as 4 subgrids of 2 power n minus 1 cross 2 power n minus 1. Consider the 8 cross 8. Okay, so this is hard to draw. 1, 2, 3, 4, 5, 6, 7, and 8. Yeah, 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Oh God. 1 second. Okay, so think so look at this basically. Okay, so look at this boundaries.
We can have 4 16 into 16 grids.
Yeah, so this was an 8 cross 8. So you can divide the 8 cross 8 into 4 cross 4 grids, right? So similarly, you can divide a 2 power n cross 2 power n into 4 2 power n minus 1 cross 2 power n minus 1. Now it is simple. So the deleted square must belong in one of them, right? So suppose it belongs in this one. So you can, so what is this? So for this, you have a 2 power n minus 2 power n minus 1 where one cell is deleted. So this can be taken care of by inductive hypothesis. Okay. What about the rest? So again, for the rest we have three full 2 power n minus 1 cross 2 power n minus 1 grids, right? So to take care of them, we have to delete one cell from each of them. You have to take care of one cell from each of them. How to do that? We will just, I lost my cursor. We'll just insert a domino here, a tromino here. Okay. What this does is that it deletes this square, and this square, this square from here, this square from here, and this square from here. Okay. Then the rest have like 2 power n minus 1 cross 2 power n minus 1 grids with one missing square. So that you can again do by induction hypothesis. So yeah, this solves the problem. Does everyone understand? Does anyone have any questions?
No, it's fine. We can move on.
Yeah, I think so. Okay. Feel free to ask any questions if anyone has any. Okay. So next, I think I'll do this problem. So next problem is, so this problem I'll actually try to show the modern coloring thingy. Okay. So suppose we are trying to cover m cross n boards with 1 cross k tiles. When is it possible? So this is a new problem. So we are trying to cover m cross n boards with k tiles. When is it possible? Okay. So first of all, note that if you are using x tiles to cover the board, sorry, what is the total number of squares in the board? Total number of squares in board. So this is I lost my cursor. Yeah, this is just kx, right? But this is also equals to mn. So you can directly see that kx is equal to mn. In other words, k divides mn. Does everyone get what I did here? Because
Yes.
x is
Yes. So like k is any factor of m or n.
yeah. So we all know that this is a necessary condition, right? Is it sufficient? Can we? Okay, so we see that, suppose call this condition star. So star is necessary. Why is my handwriting so bad? Is star sufficient? I'll just write out sufficient. So let's say, let's
Yes,
look at
it
an
is,
example.
right?
Okay, let's look at an example. Can you tile a 2 cross 6 board with 1 cross 4 tiles? 1 cross 4, I mean, when I mean 1 cross 4, they can be rotated. Okay, so like 1 cross k and k cross 1, if that was what we're thinking. So like you can use the tiles both like this and like this. So can you cover a 2 cross 6 with a 1 cross 4? So 2 cross
No,
6 is something like this. 2, 3, 4, 5, and 6.
no, it
No,
can't.
We
cannot
can't,
do it.
right?
Yes.
We can't do it. So we can't. So if you just place one here, and you can't like do anything about this, you can just place another here, right? Or if you just place one here, then you are just always losing out on these two.
Yes.
Okay. So yeah, so we see that obviously. So someone is unmute. Can you please mute yourself? There's a bit of noise. Yeah, thank you. So you see that star is not sufficient, right? So now let us think of a sufficient. So actually, it turns out that the necessary and sufficient condition is k divides m or k divides n. Okay. So this is what we will try to prove now. So I just showed you that k divides mn is not sufficient. So we will actually try to prove that the sufficient condition is k divides m or k divides n. Proof that if 1 cross k, m cross n can be tiled with 1 cross k, then k divides m or k divides n. You can understand why this is obviously like, if this holds, you can do it, right? Because if you have something like just, I don't know, so suppose k is 2 and say n is 5 and m is 6. So you can not, let's say 2 is too easy. Let's say k is 4 and okay, yeah, n is 8 and m is, I don't know, 5. Then you can just keep like the 1 cross 4 tiles like this, right? And does everyone understand why this would be a tiling of the 5 cross 8 board?
Yes.
Okay,
Yes.
yeah. So it's important to understand why this is true now. Okay, so now we will prove that if you can tile m cross n with 1 cross k, then yeah, k divides them or k divides them. So what we will do is like, so we need to have an idea of the squares, a tile squares, the tiles uh, cover. So you need to understand like what kind of squares the tile covers. So when we had the k equals 2 case, we appealed to black white coloring, right? Now black white coloring is, we saw that black white coloring was like as good as mod 2 coloring, right? So does anyone have any guesses for the general k case? We'll actually just do mod k coloring here. What do I mean by mod k coloring? I'll just show you. Okay, so what we will do is we start from the bottom most. Okay, so we write 0. Okay, so suppose this is your bottommost row, and suppose k is 4, let's say. Okay, let's do it like this. Suppose you have a 3 cross 2 board. Okay, suppose you have a 3 cross 2 board and your k is 4. So just to understand what mod 4 coloring looks like, let's just do 5 cross 5. Sorry, 5 cross 5. Obviously 3 and 2 are smaller than what was I thinking. 5 cross 5. Yeah. So 1, 2, 3, 4, 5. 1, 2. Okay. 2, 3, 4, 5. Yeah. So the mod uh, uh, the mod 4 coloring is going to look something like 0, 1, 2, 3. Right. Okay. So let's just write 1, 2, 3. 1, 2, 3, 4, and then you write 1 again. Okay, and here you write 2, and then 3, 4, 1, and then write 2 again. And here you start from 3, 4, 1, 2, and then you write 3 again. Yeah, 4, 1, 2, 3, 4, and then 1, I think 2, 3, 4, 1. Does everyone understand what the modern coloring is basically all about? So like if you had started from, oh yeah, so if you had started from like okay, so like okay, let's light it like this actually. Shit. So instead of using 1, 2, 3, 4, we will use uh, 0, 1, 2, 3. It's the same thing, right? Because you just need to have like 4 colors. In the previous, in the 2 case, we had like 2 colors, black and white. So now we'll have like 4 colors. So let's say the colors are 0, 1, 2, 3, 4. So you write 0 here, 2, 3, 4, 0, 1, 2, 3, 0, 1 2 3 0. Okay, so 2 3 0 3 0 1 3 0 1 2 1 2 3. Yeah, so this is the coloring. So now how to write this, like in a sort of closed form maybe, or I don't know, like something like in a better language, because you need to explain this, right? So suppose you number the squares from 0, 1, 2, 3, and 4. So this is just the indexing, okay, or the XY axis, if you will. So this is also 1, 2, 3, 4. So if a square is x comma y, so do you agree that we are just basically writing x plus y mod 4? That is its color. Does everyone agree with this? So this is basically how you define mod 4 coloring in a way. Does everyone see how this works?
Yeah.
Yes.
Okay, so this is called like mod 4 coloring. In general for a general K, you would just have K instead of 4. Okay, and you would call that mod K coloring. Okay, so now why is mod K coloring important? So mod K coloring is important for this case because observation that every tile contains every color exactly once. Now, why is that true? So suppose the tile started at x comma y, okay, and then it covered, suppose it was a horizontal tile and it covered x plus y, x plus 1 comma y, and then up to x plus k minus 1 comma y, right? So now note that suppose x plus y had x plus y was r mod k, then this is r mod, sorry, 1 plus r mod k, and then the next number is 2 plus r mod k, and then 3 plus r mod k, and so on till k minus 1 plus r mod k, right? So now note that these are k different remainders mod k, right? This is obvious, right? Because you have just k different stuff and they differ by 1 each. It cannot be the same thing, and hence they must represent one color, represent each color at some point. Does everyone know how this works? Why this observation is true? Do people understand why this observation is true? I am claiming that every tile must contain contain each of the k colors exactly once. Okay, to see why this is true, start at any tile. Okay, so suppose the tile starts at x comma y. Suppose it is horizontal. Okay, then it covers like x comma y, x plus 1 comma y, x plus 2 comma y. Okay, let's do it for the k equals 4 case. So suppose a tile contains x comma y, x plus 1 comma y, x plus 2 comma y, and then x plus 3 comma y, these squares. Okay, so suppose x plus 1 comma y was, let's say, 2 mod 4, right? Then what is this square? This is 3 mod 4, this is 4 mod 4, which is 0, and this is 1 mod 4, right? So you see that these are 4 distinct remainders modulo 4, and hence they must represent each of the 4 colors, right? So in the general case also we have k distinct numbers modulo k, and hence they must represent each of the k distinct colors. Does this make sense?
Yes.
Okay, so I'll move on. So now think about it, that every tile, so now we know that every tile contains each color exactly once, right? So suppose you had x tiles in the end, right? So this means that every color occurs x times, right? So what is important here is basically the fact that every color occurs equal number of times, Okay, is that always true? Look at the 5 case. Okay, so how many numbers of how many zeros do you have here? So this is 1, 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 and this is 1. How many? So 1, 2, 5, and 6, I think, right? How many ones do you have? 1, 2, 3, 4, 5, and 6. Okay, 2, 1, 2, 3, 4, 5, and 6. And how many threes? 1, 2, 3, 4, and 5. Okay. Wait, what did I do? I probably
It's
missed
present
some.
zero.
Okay, I missed a zero. Yeah. Does that
Yeah.
make it okay? Yeah, I think that makes it okay. And I think I missed a three somewhere as well. So whatever. So like you do understand like these aren't the same, right? So like you have a 7 and 3 sixes. You don't have 4 sixes. In other words, they aren't equal, right? So you cannot cover a 5 cross 5 with 1 cross 4 tiles, but we knew that already, right? Okay, so whatever. So like this is the main claim or the main part of the proof, that you must understand that every color must occur equal number of times. So now what we will prove is that, so another observation, also another observation, you note that every k columns have equal number of each color. So whenever you take k columns, you have equal number of each color. This is also kind of the same idea, because you'll see that you have like k distinct remainders per column, and hence you have like what and hence you have like equal number for each color, because like one color is just one, you can view a color as basically one residue module. Okay, so this observation also holds true. So like you can just see it from here. Suppose you take I'll just write it again quickly: 1 2 3 0 3 0 1 2 3 2 3 0 1 2 1 0 2 1 301 20230. Yeah. So now you suppose you take any like four columns, right? So suppose you take okay, just these four columns. You can just note that every one of them is present 5 times. How? Like 3 is present 1, 2, 3, 4 times, and here 5. Okay, so 0 is present 1, 2, 3, 4, and 5 times. Similarly, 1 is present 1, 2, 3, 4, and 5 times, and 2 is also present 1, 2, 3, 4, and 5 times. So this claim makes sense, right? Like whenever you have k columns, or rows are as good as columns, or k rows, they have equal number of each color. This is again because of the modern thing. So anyone having any questions regarding this? Not k color. Any questions? Okay, then I'll move on. So what will we prove? We noted that if k divides m or k divides n, then we are good, right? So now what we will prove is that if k doesn't divide m and k doesn't divide n, then this is bad. Okay. So now think about it, like yeah. So now from this observation, what can you say? So suppose we are trying to tile, suppose our k was 2, right? And we are trying to say tile 5k cross, suppose our k was okay. So suppose your k was something like 5, and you are trying to tile 5a plus 2 cross 5b plus 3. Yeah, obviously it can't be tiled because k doesn't divide mn, but let's not like think about that for a while. Just let us think about how we can optimize our structure using this observation. Okay, so you know that every time you remove so like you know that every k rows and columns have equal number of each color, right? And also you know that for the tiling condition to hold, the only thing you need is that every color occurs equal number of times. Okay, so now you note that whenever you are removing k columns, okay, you are not like disrupting the number of colors in any way. So suppose you had like number of every color was say CK was like say suppose for a color C, its number of occurrences was, let's say, FC for now, right? So when you delete K rows, or all the FCs decrease by some number, by the same number. Does everyone understand what I'm trying to say here?
Is it true if the tiles cover the grid? If and only if the tiles cover the grid?
What do you mean? Uh, okay, yeah.
Like the
No,
statement you have written.
no. Do you agree that this observation is true for all cases?
Yes. Yes.
Yeah, right. So whenever you are removing k grids, so suppose whenever you are removing like k columns, right? So suppose before, in a general case scenario, you had like when you were just initially you were starting, you had like k colors, right? So suppose uh, a given color had f of c number of occurrences. Okay. So when you are deleting k rows, you are reducing every fc for all color c by same number of times, right? So suppose your k was 5, right? So basically fc now becomes fc minus 5 for all, not 5 actually, fc minus a number of, so fc minus some number basically. So number is like whether or not depends on whether or not you are depending or a column. So some number basically for all c, and this is and this is equal for all colors. So what I'm trying to say is, like, if the tiling condition were true initially, it should be true even after you are deleting k columns or k rows. Does that make sense?
Yes.
Yes. Yes.
Okay.
Now.
Okay. Okay. This page over. Yeah. So now what were we doing again? So we were trying to tile 5a plus 2 cross 5a plus 3 with 5 cross 1, right? So you obviously know that because of the multiplication doesn't add up, you cannot have this true, but let's not worry about that. So we understood that if you remove 5 columns or 5 rows, you're good. Like, if you could do it previously, you can do it now as well. So now what I'm trying to basically say, that you can basically reduce 5a plus 2 to 2, and 5a, so not 5a, suppose 5b plus 3 to 3. Does this make sense? So you are basically modulo k and number of columns modulo k. Does this make sense? So suppose you had 12, right? 12 cross, I don't know, 13 maybe. Yeah. So suppose you can move from 12 cross 13 to say 7 cross 13, and from there 2 cross 13. And if it was true for here, it should be true for here and should be true for here as well. And then you can similarly move from 2 cross 13 to 2 cross 8, and from there to 2 cross 3. Does this make sense?
Yes. Yes.
5a plus 2 cross 5b plus 3, true for 2 cross 3. Okay. So now what are we going to prove? Like, if, so we can WLOG Mn. So now assume Mn is less than, okay, because of the above because of the above optimization. Okay. So now suppose you are trying to tile a 3 cross 4 with 5. So one thing we know is that every color occurs 5 times, sorry, not 5, 12 by 5 times. Every color occurs 12 by 5 times. Okay, this is bad. Okay, let's say 2 cross 6. Okay, let's say 6 cross 6, not 6 cross 6. This is hard to think of an example for, because you know that this is false, right? So, Okay, maybe a 2 cross 3 using 6. So you know that 6 cross 1. So you know that this, so you know that every color occurs what? 2 cross 3 by 6 times, which is basically just mn cross k. Actually, let's do 3 cross 4, then that's better off. It's okay, I'll need to use eraser. Does everyone agree with this? Right. So now what we will do is we will draw the 3 cross 4 and we will like 3 columns, 3 rows and 4 columns. 1, 2, 3. Let's draw this mod. Now let's do the mod 6 coloring. So this is 0, 1, 2, 3, 1, 2, 3, 4, 2, 3, 1, sorry, not 1, 2, 3, 4, 5. So now obviously this doesn't work, right? So now how can you like derive a contradiction for the natural case? Like it kind of would be weird to argue that like a color wouldn't appear at all, because maybe in some case it would appear. So now what happens is, like, if a color occurs too many times, that's a problem, right? So now look at the rightmost corner, okay, and then just look through the diagonal that passes through here. Okay, so this diagonal has m squares, right? And every square has the same color, right? So you are having m occurrences of some color, but you can only have mn by k occurrences. So now which is larger, mn by k or m? So can you tell me, like, which value is larger, m or mn by k? Also remember that we are trying to prove that if a color occurs too many times, then that is a problem. So yeah, can you tell me, like, okay, so note that, okay, so does anyone have any questions till this point? Just feel free to ask.
No.
Okay, so like note that mn is less than k, right? So n by k is obviously less than 1. So mn by k is obviously less than m, right? So what did we count? So what did we achieve? So what did we achieve? So we found m occurrences, but we can have only, but we can have only mn by k occurrences. Now, since m is greater than mn by k, this is a contradiction. So basically, we could have afforded only 2 colors. Now we see that there is some color which, no, we could have afforded only 2 occurrences of a color, but we see that there is some guy with like 3 occurrences. So that is a problem, right? So does anyone have any questions regarding the proof? So this completes the problem. So does anyone have any questions? So like during this proof, what we did was, like, we first came to the conclusion that k divides mn was really essential. Okay. And then we actually saw that it is not sufficient because 2 cross 6 and 1 cross 4 is a contradiction. Then I told you that k divides them or k divides them is sufficient, right? So we first saw that if k divides them or k divides them, then we can do it. And then now we will prove that that is the only possibility. So what to do? Like we'll introduce the mod k coloring where we colored x comma y square with x plus y mod k, right? And then we made two observations that every tile contains uh, exactly one square of every color. Okay, so we came to the conclusion that if you have x tiles, you have x occurrences of every color. In other words, number of occurrences of every color is the same, right? We made another observation that whenever you take k rows or k columns, every one of them has equal number of colors, equal number of occurrences of every color. Okay, so now what we did was like we will now prove that if k doesn't divide m and k doesn't divide n, then that is bad, right? So suppose you are starting with something like so basically the idea is because of the fact that every k rows and columns have equal number of occurrences for every color, we can just freely delete k rows or k columns, right, without affecting the number of occurrences. So basically the number of occurrences of every color gets reduced by the same amount. So if it were true for the earlier case, it will be true for the reduced case as well. So what we now assumed was we assumed m comma n to be less than k. So we started with a general mn and we reduced them to their modulo values mod k. Okay, do the remainders mod k. So now suppose we were trying to type. So now what happens is basically if you look at the rightmost cell and you look to the diagonal uh, coming through the rightmost cell, what happens is like every cell on the diagonal must contain the same color. Why is this true? Because of modulo values. Once again, you can just write out and check it. Okay, and then you'll see that you have m occurrences of some color, right? But you already know that you can have at most mn occurrences of that color. Actually, the color is also m because you have the color at this is just 0 plus m, right? So you have m occurrences of some color. The some color is basically m mod k, but you can have only mn by k, right? So we understood that m was greater than mn by k, so we have more occurrences of a color than we could possibly have. So that is bad, and this concludes the problem. Okay, so now I'll show you another way to tackle the problem. I think that, and then we can call it a day. So that is roots of unity solution. Okay. So did everyone follow till here? If anyone has any doubts regarding this, please ask. Oops. Okay, so now let us move on to the roots of unity solution. So roots of unity solution is so previously our colors were 0, 1, 2 up till k minus 1. Now our colors will be e to the power 2 pi I k. So suppose you call this omega, right? So suppose our colors will be, so you call this value omega. So our colors will be omega square up till omega q up till omega power k minus 1 and 1. Okay, which is basically omega to the power k. Okay, so basically you are basically using the roots of unity as colors. So again, what is the coloring like? So if you have a square xy, then you cover it with then you put the value e to the power 2 pi I times x plus y by k inside it. Okay. So now again, why is this good? So suppose you had a tile. So you had a 1 cross k tile, right? And from say x comma y to x plus k minus 1 comma y. Suppose it's horizontal, right? So what are the sum of values in the squares? So what are the sum of values in the square? So sum of values in the squares What is that? So you're basically summing up omega power x plus y minus 1, not 1 here, sorry. Omega power x plus y plus omega power, yeah, okay, I was, yeah. Omega power x plus y plus 1, omega power x plus y plus 2, up till omega power x plus y plus k minus 1, right? Which is basically omega power x plus y times 1 plus omega square plus up till omega power k minus 1, right? So what is this value? Can someone tell me what is this value, given that omega was defined as e to the power 2 pi I k, such that omega power k is 1?
0.
It should be 0, right? Why is this true? Because omega power k minus 1 is just, sorry. Why is this true? Because this value is equal to omega to the power k minus 1 by omega minus 1, and this is 0. And obviously this quantity is not 0. So, okay. So what did we find once again? So what did we find? Sum of numbers in a tile, sum of values of squares in a tile is 0, right? So now if the tiling was possible, right, what would we have? A sum of all numbers in the square is 0, in the m cross n square is 0. Does everyone follow how I reached this conclusion? If there are questions, please ask. Okay, so like we found that if you have had a general 1 cross k tile, we calculate the sum of values in the squares that it covers, and we found that that value is always 0. So what does that mean? If you have like a lot of k tiles, right? So like if you have x k tiles again, so across every k tile, so you have that sum of values of the square that is covering is 0, but it covers all. But you can place k tiles such that they cover the entire board. So the sum of values of the entire board should be 0. So now how to calculate the sum of values of the entire board? So how to calculate the sum of values of the entire board? So you know that in the I comma jth square, you have written the number omega to the power I plus j, right? So we have written this. So what is the sum of all numbers? You know that I ranges from okay, I ranges from 1 to n minus 1. I is a number, yeah, and 1 second, yeah, and j ranges from m minus 1. I think I switched the indices, sorry. Okay, okay, so now what is the sum of all numbers? The sum of all numbers is just going to be sum over all possible ij. Right. So now think about it. So like how do we write this sum? So like do you agree that this sum is the same as, so do you agree that the sum is equal to this? Does anyone have a question? So basically what happens is like, so omega power I plus j is what? So this is basically omega to the power I times omega to the power j, right? So now this summation is I, so like this summation is independent in omega to the power in sorry, in just I and j, right? So this summation is independent in I and J. So now as you vary I, so suppose you are fixing I, okay, and you are varying J, then all possible values of I plus J where I is fixed and J varies will be found. So this is basically, and similarly when you fix J and vary I, right, all possible values of I plus J where J is fixed and I varies will be found. So this product is basically this, right? Convince yourself like this is true. You can, so this is kind of like a classic double summation. So like if you have like independent functions of I and J, then you can just write it as so suppose you just had something like I equals to uh, m minus 1 and J equals to n minus 1, some independent functions of f of I and g of J for some independent functions, and you can just write something like I equals to 0 to. So do people understand this? Does is there any questions regarding this? So now basically this product is a lot more easier to write, right? So I equals to 0 to m minus 1 omega to the power I is just, this is a geometric sum, right? So it will be omega to the power m minus 1 by omega minus 1, and this is going to be, so now we want the product to be 0. So we want omega to the power this thing. So this is equal to the sum of all in the board, right? And we want this to equal to 0. So when does it possible? So this happens if and only if omega to the power m equals 1 or omega to the power n equals 1, right? But so this basically tells you that k divides m or k divides n. So are there any questions regarding the solution? Oops. So what I did was like, instead of numbers, now we are using roots of unity to denote colors. Okay, so what we did is like, so we assigned the color, we assigned the value omega to the power x plus y, where omega is 2 to the power I by k is a like a primitive root of unity such that omega to the power k is 1. Okay, so we assumed the value, so we assigned the value omega to the power I plus j to the okay, not I j here, so let's say x plus y to the xy to the xy coordinate square. Okay, and then we found that whenever we have a 1 cross k tile, the sum of values of the squares covered by the 1 cross k tile is equal to 0, right? So this basically tells you like, so now this basically tells you like when you can cover the entire board with 1 cross k tiles, the sum of values in the entire board should be 0. Now the sum of values in the entire board is quite easy to calculate. That is just sum over all I comma j possible omega to the power I plus j, and you can just evaluate this to be omega to the power m minus 1 times omega to the power n minus 1 by omega minus 1 whole square, right? So this is equal to 0 if and only if either omega equals 1, omega to the power n equals 1, or omega to the power n equals 1, right? But you already know something like omega to the power k equals 1. It is kind of easy to prove that this implies this. Okay, so are there any questions regarding this? And then, okay, so any questions regarding whatever we have covered throughout the lecture? I think, yeah, time is almost up. So if anyone has any questions regarding all the problems we have covered in the lecture, please feel free to ask now. Okay, then if there are no questions, I guess we can end it.
Yeah, ending the recording. One sec.
Yeah, yeah, sure.